Hi, in this video we will show how to derive the Schrödinger equation based on the central limit theorem. This derivation is important for two different reasons. The first reason is that we have left some elements of our mathematical demonstrations unexplained. I will soon return to this topic. And the second reason is because it is nice to understand that quantum mechanics is related to a very important theorem of statistics. Indeed, it is interesting to understand that quantum mechanics is connected to a theorem that gives a very wide universality class. So let's begin our demonstration posing the problem that we want to solve. We want to ask, what does it mean to have infinitesimal displacements delta x, and should they be really infinitesimal after all? We have used this kind of displacements, delta x or delta q, but to derive our results, of course, we have shown that other interpretations, other approaches used the time. For instance, the Feynman's path integral used the time in a sense of infinitesimal time intervals. But we want to understand what's the role played by this kind of variable. And indeed, it's important because to obtain the probability density function, the phase space probability density function, we have inverted the integral related to the characteristic function. And by doing this inversion, we have to integrate upon the variable delta q, delta x, delta q, the same thing. So we want to understand what does it mean to integrate this variable if we are assuming that delta q or delta x is infinitesimal after all. This will be answered exactly by the use of the central limit theorem. So let's try to understand how this is possible. First, let's see that we have obtained a probability density function upon phase space in our approach, which is connected to an average momentum and also to a variance. And these two results are all related to the characteristic function. This way to present the probability density function resembles a lot the same relation that we can get if we try to apply the central limit theorem. So in some sense, it induces one to at least guess that the central limit theorem is being used here in some way or another. We will show that this is indeed the case. So let's try to understand what the central limit theorem is saying in one dimension. The theorem says the following. Consider a sequence of n independent random variables, which is the y1, y2, etc., with averages given by these values, mu y, and invariance given by sigma I squared, and put the y as the sum of these random variables. Then, and under very general conditions, the reduced variable, which is represented by the y displaced by the average and divided by the variance, which are variance and average given in terms of n, we'll make this n goes to infinity, has approximately a Gaussian distribution with the average equal to 0 and the variance equal to 1. Thus, if Fn is the probability distribution function of the random variable y, which is the sum of random variables, then we have in the limit, when we make n goes to infinity, this Gaussian here, which is exactly the Gaussian that we have obtained in our derivations, but here expressed in just one dimension. So let's try to demonstrate this theorem. And we begin by assuming the following situation. We have random variables. Note that we are talking about random variables without any problem, because we already know that quantum mechanics, in this approach at least, is related to random behavior. So let's assume that, for example, we have just three random variables and we are trying to go from one point of the configuration space, which is y, to another point that is y plus dy. This dy is finite, okay? Okay, there are many ways in which we can do that. We can sum these variables in a number of ways using the constraint that we must go from y to y plus dy. This is what is being said here in this expression. The summation can be in any way, but it must be within the intervals of y and y plus dy. So what we are trying to do is to calculate the probability of our particle or entity, if you prefer, going from one point of the configuration space to another point by means of a number of trajectories or paths. Note that this resembles a lot the way by which Feynman gets his results on Feynman path integrals. We know that since each y is independent, the probability density function is given by these w's, we know that the overall probability must be given by the product of the individual probability. And of course, we have to sum them to the extent of some values, which is, for instance, here and here, here and here, and here and here, in such a way that the summation of them will give exactly dy. But note that this way we write the expression is very hard to work, because these limits of the integrals are variables. So to remove this problem, we can use the fact that the summation must be always equal to dy, and use Dirac delta function to ensure that this will be indeed the case. Then, in this case, of course, we can now remove this integration in the individual displacements and integrate over all the space. So we get this expression here. This expression is very important because now we will express this delta function in terms of exponential, which is indeed very well known. We can express this in these terms. This is a Fourier transform of an exponential, and we get then the probability density function that we have written in the previous slide in this way. Now each probability is given by this expression, and note that this expression resembles very much our characteristic function now written in terms of t. We know, of course, that in our case we don't have t, we have a delta key, but it's the same way formally speaking. We then define this term as the characteristic function, and we see that the probability density function is indeed the product of equal terms given by this expression. Note that this expression does not depend on the specific way we define y, and they are all equal. So we can write the probability density function as the Fourier transform, which is natural when we talk about characteristic functions, of the product of the individual characteristic functions which are equal. Then we can say that we have a characteristic function of the whole interval for the variable y, which is given by this product. Okay, it's very important. We can now make a rescaling of the variable just to make it appear the average. We are assuming here that this is the average in terms of variable k, variable y, k, and also the variance here. So doing that and doing a lot of mathematics, I won't do that here, it's not the important result. We finally find this result, which is the logarithm of the rescaled characteristic function. Note that here we have a very nice result. This term cancels out with this one. When we make this with the square of this term, it gives m squared divided 1/2 divided minus, but then we have a minus here, so it gets plus n s squared t squared. These terms cancels out with this one here, and we get just s squared over s squared, this cancels, and n cancels with this, and we get, apart from the other terms, just the term minus t squared over 2. The fact that we have other terms here, this r, which is a term depending on n, and this one, and also the square of these other terms, is very important because it indeed justifies the fact that we have developed our function up to second order in our derivations, because we can show that all these terms goes to 0 with n to minus alpha, where alpha is some number greater than 0. So in the limit, when we make n goes to infinity, these terms all goes to 0, and we have then only the fact that logarithm of the characteristic function, the rescaled characteristic function, is minus 3 squared over 2, which gives indeed our probability density function as a Gaussian with variance 1 and average 0. But what does it mean to make n goes to infinity? And this is why the central limit theorem is also called an infinitesimal theorem. This means that since we are assuming that dy is fixed, to make n goes to infinity in this summation, represents to assume that each y going to 0, and so are assuming what we called an infinitesimal value. So the very content of the central limit theorem is that after the second order, the fact that we are summing n going to infinity number of random variables represent the fact that we are not losing terms if we goes on only up to second order. And this is why we could make our developments up to second order, and also Feynman's too, and also in the stochastic derivation. So what we get, we have already said that, is a distribution function, probability distribution function in terms of t. And this is in fact the way by which we demonstrate the central limit theorem. So we have seen the demonstration of the central limit theorem, and from the previous videos in which we have demonstrated the derivation of the Schrödinger equation based on the characteristic function, I think it becomes very easy to understand in which ways the present derivation connects itself to the derivation of the Schrödinger equation. This result I will be showing in the next video, in which I will present the relations between the derivation of the central limit theorem and our own derivation of the Schrödinger equation. Thanks for watching.